together, what percentage of the acid ionized in this 0.03 molar solution. So to try and answer this question, we recall that, like I have always emphasized to you, we have to know the formulas of most of these compounds, especially organic acids. We'll give you all sorts of names. We could give you a name such as octanoic acid, decanoic acid. We have to know what the formulas for these acids are supposed to be and what their ionization equations are supposed to be. And also, if you remember the concept of basicity, whether you are dealing with monoprotic acids or polyprotic acids. So you recall that we had used a formula at some point where we said whenever a weak acid, and if you were given the Ka value, such as in this case, all that you needed for you to be able to find the concentration of hydrogen ions would be to find the multiple of the Ka value and the concentration given initially for sorry, phone is ringing for a friend. Yeah, the phone is ringing. Okay, yeah. So we said we would have to multiply the Ka value and the concentration of the acid that you will have given. Then you have been given. Then you find the square root of the multiple that will give you the concentration of the hydrogen ions in solution. Then after we will have found the multiple of the Ka value and the concentration that were given initially for this particular acid, and we find the square root of the multiple, we are getting 1.34 times 10 to the power negative 3 molar concentration. So this is the amount that dissociated from this particular acid, given that the acid is a it's a monoprotic acid. Okay, only one hydrogen atom will be given out per molecule of these species. That's what this means. So the amount that will have dissociated from the acid will be equivalent to the concentration of the hydrogen ions in solution, provided there are no any other sources of hydrogen ions. And you recall that the contribution that would come from water molecules as a result of the auto-ionization of water molecules, that usually is ignored. So we're going to assume that all the hydrogen atoms that we have, or rather ions that we have in this particular solution, are coming from the acid itself. So the amount that will have dissociated against the initial concentration that we are given, multiplied by 100%, this gives us 1.34%. So you can see that for strong acids which undergo complete ionization, the molecules that would result onto the other side of the equation, which is the right hand side of the equation, would have come from the initial molecules into a 100% extent, meaning that those are not going to be there. But when you compare with a weak acid such as this one, only a very small portion of 100% will have undergone dissociation, meaning that the rest of the percentage should be composed of those molecules themselves. So this particular acid at that temperature that we are given only undergoes, or rather this particular concentration will only undergo with the Ka value as given, will only undergo dissociation to a 1.34%, quite a very small percentage that is. Okay. So when we look at the next question, you see that for part B, we are told that a student prepared this molar solution of formic acid, and its pH was found to be that at 25 degrees Celsius. So you remember the logarithmic form of the equation for finding pH. So when it is changed to its exponential form, it changes to that. So this is the exponential form of the formula that we use to find pH. And the dissociation equation for formic acid, it's going to look like that. So formic acid also is a monoprotic acid or monobasic acid. So when we substitute into this equation where there is pH, we put that value there, into the equation, the hydrogen ion concentration is found to be 2.14 times 10 to the power negative 5 molar concentration. So the concentration of formic acid that we were given initially was 0.03. So we want to establish what the concentration is going to be at equilibrium, because the question is asking us to find the Ka value. The Ka value is supposed to be computed from the law of mass action, which would come from the dissociation equation for this particular acid, which is supposed to be in this form. But we have to know what the concentration was for formic acid at equilibrium, and that is why we are substituting here. This is the change here. The change is minus because in relation to what the concentration of formic acid is supposed to be. That is why this amount of hydrogen ions in terms of more concentration, since it is known, it is supposed to be subtracted from the initial concentration, and that is why we're subtracting here. So that the amount that we come up with at equilibrium is going to be substituted into this equilibrium expression to to find the value of Ka, as we are able to see there. So you see that the concentration of hydrogen ions and the concentration of formate ions, the two concentrations are the same. That's why we have that concentration and that one. Then we are dividing by the concentration of what would have remained in solution of formic acid, and we see that the Ka value is equal to that value, equal to 1.53 times 10 to the power negative 8 with no unit. Don't add any unit at this stage. What percentage of the acid is ionized in the 0.03 molar solution? So this will be computed by using the amount that will have associated, rather dissociated, in relation to what we were given initially. So when we substitute, we see that the percentage is quite small, which is 0.0713%. Unless otherwise stated, recall that percentages are to be given to one decimal place. So essentially, this is just 1.0, or that is 1.1%. But of course, this would be more accurate than expressing our percentage to one decimal place. So for such type of questions, because the answers would have been found before you are subjected to the questions, so we will specify the number of decimal places to which we would want the percentage to be expressed. So we'll tell you, express a percentage to 3 significant figures or maybe to 2 decimal places. Okay, so notice that for weak acids, percentage ionization decreases as the concentration increases. So the higher the concentration, the less your acid is going to dissociate. The more it is diluted, the higher the dissociation in terms of the percentage. Okay, that's how we're supposed to answer these questions. We look at a slightly different aspect, the aspect of buffer solutions. So when we are looking at the previous topic, chemical equilibrium, you probably must be able to remember that I had mentioned, alluded to this particular concept of buffers, where I'd actually even given you an example of a natural system where we have some buffering of some sort, which is our blood. The pH for our blood is constant. It doesn't change irrespective of what type of food that we might have taken in, whether the food is acidic or basic, the pH stays the same. So a buffer is a solution which can resist changes in pH on addition of small quantities of acid or alkaline or on dilution. So this is a system which is able to defend itself, whether it is subjected to an acid or an acidic solution or a basic solution. But of course, there's a condition here. It says a small quantity of an acid or alkaline or on dilution. So you are not to add an entire ocean of an acid to a buffer, and you'll expect that your buffer is going to be able to withstand such a change. It will definitely collapse. The condition is that the changes should be quite minimal. And if these changes are very minimal, that would have been brought about, your buffer solution will be able to resist these changes. Okay. So how then does a buffer work? So a buffer is going to work as follows. A buffer solution is a mixture of an acid and an alkali. So the composition of a buffer should be that you should have an acid and an alkali. I'm sure many of you are asking a question to say, well, a solution of an acid and an alkali, how is this possible? Because we know that when we mix acids and bases, they are going to react to form a salt and water. So then how is this possible? So we're going to discover how possible this is very soon. The acid neutralizes, so the way the buffer works is that the acid is going to neutralize the alkali that is added, and the alkali neutralizes the acid that is added. Okay, so it works both ways. That's how buffers work. When you bring an alkali, the acid will perform its function and neutralize the alkali. When you bring an acid, the alkali will perform its function and neutralize the acid that will have been added to this particular buffer solution. The mixture cannot be of a strong acid and a strong alkali. Take note another condition yet still. Okay, do not try to create a buffer solution using a strong acid and a strong alkali. Otherwise, they would simply just react with each other, and you're going to form a salt, water, and it will not be able to perform its desired function as a buffer. So what are we to do then? An ideal mixture for this purpose is a mixture of a weak acid and its conjugate base. Okay, so sometimes you may be required to explain how is a buffer created. So you or formed, you're going to have to make sure that you mix a weak acid and its conjugate base, or you mix a weak base and its conjugate acid, okay? Or a weak base and its conjugate acid. So those are the two mixtures that you might have to use to create a buffer solution. Substances which can behave as both weak acids and weak bases buffers. Examples of buffer solutions, you can get acetic acid, which is ethanoic acid, and its conjugate base, which can be formed using, that is sodium acetate. This is sodium acetate. And the solution itself is acidic in a way. Okay, it's acidic in a way, but of course it will be able to perform the functions of a buffer, whether we bring in an acid or we bring in a base. So acetic acid and its conjugate base, which is sodium acetate. You can create a buffer that is going to be basic in nature, but of course it will perform its functions perfectly well as a buffer. So you can get ammonium chloride and ammonia. Okay, you mix these two. That is your base here and its conjugate acid, which is this one. So the base, which is ammonia, and the conjugate acid, which is ammonium chloride. So a combination of these two, they will work perfectly well. This is an amino acid, alanine. Okay, you probably, I'm not sure how far you have gone with your biology, but you should have been introduced to the 20 amino acids that we focus on mostly whenever we are teaching biology to first years at the university. So this is alanine. Alanine, this is the alaninate ion. The alaninate ion can be gotten from its salt, a salt of this particular compound, which can be potassium alaninate or even magnesium alaninate. You can use magnesium alaninate or potassium alaninate and alanine itself, or alanine. Some people would pronounce it as alanine. Alanine, alaninate, alanine, alaninate, potassium alaninate. Yeah. So those are some examples of buffer solutions that you can use. How does a buffer work then? So we want to understand how a buffer works in case you are given a question where you might be required to explain how a buffer works. So this is how you are going to explain how a buffer works. It works by resisting pH change on addition of acid and alkali. So it's going to resist pH change on addition of acid and alkali. So these mixtures will react with acid and alkali as follows. So we want to see how this is possible or how this takes place. Examples, when you have a buffer that is made up of acetic acid and sodium acetate, how is this one going to resist changes in pH? So the resistance in changes of pH will occur as follows. So you have your acetic acid in solution. Then to this solution, there is a base that is introduced in small quantities. Okay, so the way the buffer is going to protect itself or resist change in pH, it's going to donate. So the acetic acid molecules will donate their protons to hydroxide ions that would have been brought about as a result of addition of a small amount of a base to this particular solution. Then when these donate their protons to the hydroxide ions, they are going to form acetate ions, and you have water molecules, in which case this base would have been neutralized by forming a molecule of water. Recall how neutralization was defined when you were back in secondary school. Neutralization is a reaction in which hydrogen ions of an acid and hydroxide ions of a base react to form a molecule of water, and this is what we are seeing here. Yeah. So when you introduce an acid on the other hand, recall how acids donate or can donate their hydrogen atoms to water molecules to form hydronium ions. So this is a hydrogen formed as a result of the acid that is introduced into this particular reaction mixture. Okay, they donate their hydrogens, the water molecules form hydronium ions, and these are going to give this particular solution its acidic characteristics. So whenever these are present in solution, the acetate ions from the sodium acetate, which are present in this particular buffer, will interact with the hydronium ions and abstract protons from them to reform acetic acid molecules, which are actually just part of this particular system itself. So those will interact with those to reform those, which is what we have here and there. Then you will have formation of water molecules, some neutralization kind of arrangement. So the buffer will work in this particular manner to try and balance up the concentration of those and the concentration of those in solution, even when you would have introduced in solutions that are acidic or solutions that are basic, or solutions that are acidic or bases and acids themselves. So the solution manages to protect itself by making sure that the pH is maintained at what it was. So one of the labs that you'll be expected to do as first years would be to try and test. You'll be expected to form buffer solutions, and then you carry out experiments to try and see how buffers are able to resist changes in pH. So we've got digital pH meters that you'll be required to use. with which you'll be able to measure the pH in real time. They are quite delicate. You may not really be able to use them as individuals. You probably are going to have to use them in groups, maybe in groups of 4 or 5, laboratory demonstrators or the technicians found in your prep room there. Okay, so you form these solutions, then the buffer solutions use mixing all those examples of compounds that we are giving you here. Then you get the probe of your pH meter, you put it in your solution, then you start to add small amounts of either an acid or a base. So you're going to be seeing, the moment you add a small amount of an acid, you will see the pH maybe rises or drops. Then after some time, it stabilizes and gets back to what it was. So you'll be able to do these experiments and be able to see how buffers actually work in terms of how they resist pH changes. Okay, yeah, and of course you might be expected to explain all this in case a question is given in your quiz, any of your quizzes, or in your test, or even in the exam. We can throw in anything. We simply just ask you a combination. These two substances can be combined to form a solution that has got some buffering capacity. Okay, in brief, explain or describe how this particular buffer solution can resist changes in pH when this amount or a small amount of an acid is added or a small amount of a base is added to this particular solution. So you'd be expected to write these equations, because with these equations, your explanations would make much more sense than you just writing everything in words. Or well, if you're able to explain everything without the use of equations, your answer may still be correct, but we may be expected to throw in some equations to try and show how this is taking place. Okay, good. If you had an example of a buffer solution that is composed of ammonium ions, which may probably come from ammonium chloride or any other ammonium compound, salt, and you've got ammonia. So your base there and its conjugate acid mixed together. So when we bring in a base into this particular solution, the ammonium ions would interact with the base to form, by donating a proton to the hydroxide ions of the base to form ammonia and water molecules. Thereby, the system would have somehow managed to defend itself. If we bring in an acid, hydrogen ions from the hydronium ions will be surrendered to, the ammonium ions, the ammonia molecules to form ammonium ions and molecules of water. So like I said, you need to be able to write these equations to try and explain how buffers manage to resist changes in pH. Okay. Buffers can also resist change in pH on dilution. So supposing you did not add an acid and you did not add a base either to this particular buffer, how then would the buffer, instead, if you did not add an acid nor a base, but you added water to this particular solution instead, in a manner of, in a way of trying to dilute it, when you try to dilute it by adding water molecules, how then is your buffer going to manage to resist change in pH? So this is the way this is going to happen. On dilution, both the weak acid and weak base can dissociate more to compensate for the dilution. So when you add water, both the weak acid and the weak base can dissociate more, okay, to compensate for dilution. So this is the way this is going to occur. You have your solution which contains acetic acid, okay, which is a buffer. When you add water to this particular solution, recall how we had explained that water is amphoteric. It can behave as an acid or a base. So when you subject it to a system that has those molecules in it, the water molecules would behave as though they were like they were molecules of a base, and they're going to abstract protons from the acid to form acetate ions and hydronium ions. Okay. If any of those should be present in a slightly higher amount, the acetate ions from sodium acetate would interact with the water molecules by abstracting. They're going to abstract protons. Okay, they will abstract protons from the water molecules. So the water molecules in this case are behaving as though they were molecules of an acid. So they will donate protons to the acetate ions to form acetic acid, and you're going to have hydroxide ions. So the system is going to balance, the pH. It's going to resist changes in pH by balancing up the molecules present in this solution in terms of those two that are there. So even when you add water, the pH will not change significantly. So in that experiment that I talked about, we will tell you, add so much amount of, so you may have to maybe form 3 different solutions with the same quantities dissolved. So you've got your buffer with the same constituents or components in one beaker labeled beaker 1, another one labeled beaker 2, another one labeled beaker 3. So in beaker 1, you may be given the quantity of an acid that is supposed to be added, but of course we'll tell you, add small amounts at a time. Then when you'll have added everything, you're going to notice that, well, the quantity that you'll have added is going to be slightly significant, but the pH still remains the same. Then we ask you to shift to the next beaker, which is labeled beaker 2. Then we tell you, add this much of a base. Then when you add, in the last one, you add this quantity of water. Then we ask you to draw some comparisons or some conclusion. Most probably the conclusion is going to be that in neither of the beakers are you going to have a significant change in the pH. Maybe it's just by a 0 point something change that you probably might notice in 1 or 2 of the beakers that you have given. An indication that indeed buffer solutions do manage to resist changes in pH, whether you have added an acid or you have added, you will have tried to neutralize the buffer or dilute the buffer solution, that is. Yeah, good. So the same thing will happen here. In the other example that we gave, you see this one donates its protons to this to form those, and ammonia, you have the ammonia molecules interact with the molecules of water to form ammonium ions and hydroxide ions. One other aspect then that we might want to also pay attention to is what we call the calculation of pH of buffer solutions. So we want to be able to calculate the pH of buffer solutions, and we use the Henderson-Hasselbalch equation for this particular purpose. So this equation will show the relationship between a buffer's pH and the relative amounts of the buffer's conjugate weak acid and weak base. It can be used to estimate the pH of a buffer solution, and it is derived by rearranging the acid dissociation expression for the conversion of a weak acid into its conjugate base, so that the expression is given in terms of pH. So that's the Henderson-Hasselbalch equation that we're going to have to use. So you need to know the Ka value of your acid, which is the acid ionization constant. Then you find the pKa value as though you are finding pH of the Ka value, which is the pKa value. We have seen this before. Then you add to the log of the ratio between the concentration of the conjugate acid, the conjugate base, and the conjugate base and its acid. So the acid there, its conjugate base, the ratio, the logarithm of the ratio, then you add to the pKa value. So we need to master this particular equation. A few equations may be given to you in your test, but of course not in your quiz, and maybe in the exam also. We're not saying we're going to give you all the formulas, no, but some of the formulas might be given. But it would be a good idea for you as a student to make sure that all these formulas, you put them in one place. You master them, in other words. Then it becomes very easier for you to answer questions because you're not going to keep flipping pages to check where is the formula that they might have been given. If you already have it in your answer questions. Okay. So buffers help to keep the pH constant, or nearly so. So you probably might notice that even with the experiment that I was talking about, you may notice some slight changes, but the pH is not going to change that much. Okay, so this is what this is basically about. So we see that we have the ionization equation for a general acid with that formula there, resulting in 2 protons and conjugate base. So the pH is going to be given by Ka value. This is basically what we're talking about. So you've got the conjugate base and the acid here, which we also defined as a proton acceptor, and you've got the proton donor. So yeah, we would do it to remember all this. The example that we might want to look at, we've got an example here where we have an aqueous buffer for analyzing. So we have an aqueous buffer for analyzing the various ions in rainwater. Is prepared and has equilibrium concentration of 5.0 times 10 to the power negative 5 molar boric acid, and to the power negative 5 molar borate. So borate is base of boric acid. So using the Anderson-Hasselbalch equation, estimate the pH of this solution. So here, this is for purposes of showing how this is supposed to be done. In your test or quiz or exam, will not tell you what formula to use. We'll simply tell you calculate the estimated pH for this particular solution at 25 degrees Celsius. So the Ka for boric acid is 5.79 times 10 to the power 10. And the pKa value, which is computed using this equation here. We remember this equation, we have seen it before. So using this equation here, you find that the pKa value is 9.237. So when we get this value, we throw it into this equation here, and we get the concentration of the conjugate base divided by the acid concentration of the acid, and we compute these numbers. We will find that this solution is going to have an estimated pH of 8.84. Okay. So another way of how these questions may be asked, we will give you the amounts of the weak acid and its conjugate base. Then we'll tell you, determine whether this buffer was an acidic buffer or a basic buffer. So you would have to do all these calculations. Then looking at the pH here, you see that this is beyond 7.0. So this buffer that was used was a basic one. It was a basic buffer. Okay. So in your free time, you can try to answer these questions. So I'll give you 30 seconds to copy the questions for those of us that might not have hold of these questions, or you can simply just take screenshots for those of us that are able to do that. Then we will proceed after 30 seconds. Okay, 30 seconds are up. We can continue. One more example to try and understand what we're talking about here. Calculate the pH of a buffer prepared by adding 10 mUs of 0.10 molar acetic acid to 20 mUs of 0.10 molar sodium acetate, which is its conjugate, excuse me, base. The Ka value is given as 1.75 times 10 to the power negative 5. So the equation that we have to use is this Henderson-Hasselbalch equation, where pH is equal to pKa plus the log of the concentration of the conjugate base compared to the concentration of the acid itself. But notice the way the question is designed. We've been given the amounts of these in mUs and their concentrations. Okay, so when we are mixing these two, the concentration that we have been given for acetic acid, when we mix it with something else, is going to change. So we can't use this concentration here, okay? And we can't use that concentration there. So you see that as we keep on adding a few more details to the concepts that we have, such that at the end of the day, like I pointed out to you the time when we met, all these concepts are going to be put together nicely. And then I generate one very serious question. Of course, not too complicated a question for you guys to answer, but it would be a question that should be up to the standard that is expected. Okay? A question that we are supposed to answer as the university students, such that when we are able to answer these questions, we'll be sure that we have students that are able to remember the concepts that will have been presented to them. And we're going to have students that are not going to struggle when they go to work in the mines, whenever they are going to have to work elsewhere. That is, they will be able to work in the lab if they are put in a lab where they need to do, these to carry out chemical reactions to determine the pH at which chemical reactions are supposed to be carried out. Some of you would work in industries where food is being manufactured. Some of you will work in places where minerals are going to be extracted. Others may find their way elsewhere. But if you're going to be found in a place where you need to carry out chemical reactions, definitely you may need these skills. You should know the conditions under which your reactions are taking place, and that's why we're teaching you these things. So you first find the number of moles of acetic acid. Volume. So when you multiply the concentration and the volume, you will have the number of moles of acetic acid. Okay, so to find the actual concentration of acetic acid after it will have been added to sodium acetate, you're going to use the total volume of the acetic acid and the volume of the acetate, sodium acetate, which is 20 mUs, which gives you a total of 30 mUs. Then you're going to have the number of moles that you found here and the total volume. It will give you the concentration of acetic acid in this solution. So when you find the number of moles of, this sodium acetate. Okay, sodium acetate, that should be small letter n here, not capital letter N. Okay, kindly just make that slight modification for me. And it should be small letter n here. So the number of moles of sodium acetate multiplied, that is the concentration given initially, multiplied by the volume that we were given. The number of moles is 0.002 moles. Then we use the total volume against those number of moles. We find that the concentration of sodium acetate in this particular solution is going to be equal to 0.0 0.67 molar. So now if for some reason you rushed into using that concentration and that concentration, the answer that you're going to find was going to be a wrong answer. So be very careful. This is why I kept telling you guys that those of you that have been consistent in attending these online learning sessions, you are likely to do far much better than our friends who, unfortunately, for some of them, it's not because they do not want to attend these learning sessions, but it's because they may not have the smartphone that you guys have. They may not have access to internet connectivity, which is as strong as the one that you guys have. They may not even have bundles, some of them. So we do not blame them for not attending these sessions. But there's still a small portion of the friends can't attend these learning sessions because they feel intelligent. Okay, we will meet them in the exam. Don't worry about them. But for you guys, I assure you, it will be very easy for you to answer questions. Okay, yeah. So we have just give me a minute, a minute. Okay, just okay, good. We can continue. All right, sorry about that. Yeah, so you find those concentrations, then you throw that into the equation, the negative log of the Ka value here, which is A, plus the log of the ratio, the log of the ratio, which is going to give us okay. Sorry, you guys. There's a phone call that keeps coming in. You kindly bear with me. Let me just just give me a minute. Okay. Okay. Yeah. So it's done. Sorry. So you. Okay. Okay. Yeah. So we find the answer as 5.1 as our answer there. Just move this. Okay. Then we proceed. Okay, yeah. So the buffer's capacity, we calculate the one more example. Calculate the pH of 0.20 molar ammonia stroke 0.20 molar ammonium chloride buffer. What is the pH of the buffer after the addition of 10.0 mils of 0.10, that is 0.10 molar HCl to 65.0 mil of the buffer. So the Kb value is given as 1.80 times 10 to the power minus 5. So the pH can be computed by pKa plus the log of the concentration of ammonia and ammonium chloride. So in the question, you have been given the KB, you've been given the KB value. So you will need to find the, you will need to find the Ka value. So the Kb value is given. I mean, the Kb value is given, but you do not have the Ka value for you to use in this particular equation. So the relationship between Kb and Ka is that you have to multiply Ka and Kb for you to get the Kw. You remember this Kw was dealt with, we dealt with this at some point. So we divide the value of Kb into Kw for us to be able to find the value of Ka, which is given as 5.6 times 10 to the power negative 10. So now that we have found the value of Ka, we can find the pH.
Sir, we can see screen.
Screen is not visible anymore.
Yes, sir.
Okay, let me try to reproject. Let me try to reproject then. Okay, just give me a minute. Let me project then. Okay. Okay. Yeah, this was supposed to be there. So we just have this as our last example to look at, and then we will surely call it a day. Okay. Yeah. So we. Okay. So we find the value of Ka, then we put it in this particular equation. Then we find the pH as 9.25 for this particular question. Then one last example question. What is the pH of the buffer after the addition of 10, the last part of the question, that is, after the addition of 10.0 mils of 0.10 molar HCl to 75.0 mils of the buffer. So we have, in the previous slide, you noticed there was 70, that was 65.0. So this was a typo. It's supposed to be 65. So we correct this one, 65 of that one. So the initial concentrations for ammonia, we have the concentration that we have been given here, which is 0.20 against the solution itself, which was 65. And then we change it to decimeter cubic. We find that we have 0.0130 moles. Then the ammonium ions, we have the same amount of solution. Of course, here this is given in liters, but of course, it's the same thing as this particular number that we have there. Yeah, multiplied by the concentration, we get the same number of moles. Then for the HCl that we added, the hydrogen ions, we have 0.10 times, that is times 10 to the 3. This is, okay, so it's a 10 mils. It's a 10 mils, which is changed to decimeter cubic. Then we have 0.0010 moles. Then after adding the acid, we have, you see that the number of moles of ammonia, okay, the number of moles of ammonia, we're going to have that concentration that we have there, okay, that concentration that we have there, minus the concentration of hydrogen ions that we have here, which is going to give us those number of moles. Then this number of moles divided by the total volume, because we had 65, and then we added 10 mils of HCl. So the total volume of the solution now becomes 75 times 10 to the power negative 3, which is supposed to be in liters. And this is the concentration that we are going to have for ammonia. Then notice something for the ammonium ions here. The ammonium ions will add acidity to this particular solution. Then the hydrogen ions also will add some acidity to this particular solution. So the number of moles of ammonia plus the number of moles of hydrogen ions, okay, this is going to be considered as something that is bringing about acidity to this particular solution. So the total number of moles becomes that. Then the number of moles divided by the total volume, that is going to give us the concentration as 0.19 molar. Then using this particular equation, we're going to have the pKa for this particular acid, for the acid that was given, and the ratio of the number of moles that we have found. Then we take the log of that. We see that the concentration is going to be, the pH is going to be 9.19. So the initial pH was found to be this 9.25. Then after adding 10 mils of a very strong acid, but of course a small amount, which was just 10 mils, the pH drops slightly to just that. But you can see that this number and the other number, the difference isn't that much. So the buffer solution manages somehow to protect itself. It doesn't change as much as you might expect it. So these are the type of questions that we will be expected to answer. And my good friends, at this point in time, I can, safely say that I have taught you guys chemical equilibrium, or at least what was left of the topic that you were doing, and also acid-base equilibrium. And I expect that surely all of us will be able to answer questions effectively in your test that you are likely to write as soon as you return to campus, as well as your final exam. I wish you the very best, and I'll see you for the next topic that we are going to have to do. I'm sure most probably after 2 topics, I will still come back to teach you the topics that will follow. For your notes, I will make them available as soon as I manage to sit in one place. I'll send them to your representative, and then the representative will share them with everyone. Enjoy the rest of the day.
Yebo.
Thank you.